Hello, my name is Jin Yang. So this video is to demo how to use the MATLAB code, the augmented Lagrangian digital image correlation, or I call it ALDIC. So before we start to introduce this method, just a quick recall, what's the digital image correlation? So DIC is the experimental method to measure full field deformation. So for example, usually we paint the sample surface with some speckle pattern, and we use the high-speed camera to track the image. And then we use some image tracking algorithm, we can solve their displacement field, and then we also get their strain field. And here the ALDIC is the most accurate and robust image tracking algorithm. So you can Google the MATLAB file exchange, the augmented Lagrangian digital image correlation. You can find this code here, and you can easily download it here to click this button. It will automatically download the code. Or you can go to the GitHub. You can to see the code directly there, or follow our code there. Also in the code, there is a menu to guide how to use this code. So after the download, you just unzip this folder, and you will find that there's a menu file. And this menu has all the information, like for example, where the address for this code and for the original paper, and how to use this code. So you can put the code in the MATLAB, and for example, in the 2D ALDIC, and then you can open the min file. It's called the min ALDIC. So the code is run like section by section. So once you are familiar with all the sections, you can just run it once. So first, I will introduce this code. I will run it section by section. So there's the button here. So for example, if I run the first section, so I will set up the max compiler for the MATLAB to use the C++, the C code. And also I will add path to those subfolders like function, source, plot files, and some other folders. And in the MATLAB command window, you will see there's a message called the max is completed successfully. So if this step doesn't work, I will recommend you go to the menu, so where I list how to fix this problem, like in section 3, which is about the MATLAB max setup. And also to do the DIC, you need some images. So for example, you can put these images into a folder. For example, here I have the images of the heterogeneous fracture. The image format can be PNG, JPG, TIF, TIFF. They all can be used. And also, I will demo first just the 2 frame of those. And this is the heterogeneous fracture definition. So I run the second section, so I will read this image for the load the DIC images, and also I will define some DIC parameters like the size of the window and the spacing of the neighbor windows, etc. So let's run this section. Okay, so here there are 3 options you can to load the images. You can just select the image folder. You can manually to select the individual images, or you can use the prefix of the image names. Just keep in mind, you need to put that folder on the MATLAB path already. So for example, here, I can just manually select some images. So I will select the reference image, that's the 4 zeros teeth. And the next, I will select the deformed image, that's the image 0570 teeth. Okay, so in this case, I only select the 2 images. And after I load those images, so there will be a window will pop out for me to define the region of interest. So I can define the top left and the bottom right. So you can try other arbitrary mesh, but here the demo is only for the very nice rectangular domain. And here I choose the subset size is about 20 pixels. Usually the subset size is the sum length. You need to have 3 to 5 features of those patterns. So it can be some speckled dots or some, some lines, some features to include within one subset. And also for the subset spacing, usually it's about like 1/4 to maybe the same of those set size. So here, usually I just choose half of those. So I choose the 10 pixels at my neighboring subset step. Okay. And the ALDIC, the hybrid method, so it's both the local step and the global step. So in the global step, I need some global solver. So you can use the find the difference or find the element. You also try forward transform, but here I implemented the find the difference find the element. So if for this mesh, there's no big difference. So I just use the find the difference because it's a little bit better than the find the element for the boundary effects. Okay, let's try to find the difference here. And since ALDIC is the hybrid method, so in the local step, you can use the parallel computing. So you can set up the parallel pools, use the MATLAB parallel computing toolbox. So if you don't have the parallel pools, you could just use the single cluster. So you can input 0 or 1. If you have more than one, you can just use larger than one number. So here I just try 2 for my computer. Okay, so this section is done. So if you want to load other images in this folder, for example, you need to easily to add this folder, add to the path. And then we come to the main part for the ALDIC. So the FFT to compute the initial guess. And then the local step for the subpop 1, global step for the subpop 2. And then we enter the alternating direction method of MATLAB through the ADMM iterations. So we run this section. Okay. And then first we compute the initial guess. So initial guess, we use the fast forward transform to maximize the cross correlation. So usually it's computed very fast, just a few seconds. Yep, and then you will have the initial solution. So it's a little bit noise, but it still looks very nice. And then you go to the first local step. We use the parallel computing. So here I use the 2 clusters. So it computes very fast. And there are like 4% of the bad subsets. And you can manually click those bad points. So usually, if the definition already looks very nice, for example, like this, you don't need to manually click those bad points. You can just press the 1 or just press the Enter key to skip this step. If you want, you can just input, for example, 0. So look at the definition. So it gives some upper bound and lower bound for the X displacement and then for the Y displacement. So here, for example, I input the upper bound about 20 and I input the lower bound about -30. So if you don't have this upper bound issue, you just skip this part at all. So it's okay. And for the Y displacement, I input the upper bound at -50 and the lower bound is about -70, for example. Okay, so it will ask you, do you want to reset lower upper bounds? You can press 1 or enter key if you are satisfied. Okay, and then you can manually click some local bad points. If you feel there's no local bad points, you can just press 1 or the press enter key to skip this step. So here, I just to show you, if there are, you can just press 0. And then there will be an image pop out, so you can manually click, you see those local bad points. So after you clicking all of those, just press the enter key. So it will ask you to check if there's still any other bad points. So until you are satisfied, you just press 1 or just press the enter key. So similarly, you will do this for the Y displacement. So here I just press enter key to skip this step. And then we go to the global step. This step usually is super fast because it's a very nice solver, even in the global problem. So after that, we will go to the ADMM iterations. So in the section 6. Yeah, it's very fast. And at the same time, you have some temporary solution for the global step. You see, this is the convergence very fast. And if we see the convergence of the subsets, they also increase. So now that subset is about the 2%. And also if you check the update of the local step, the update of the global step is also quite smaller, like 0.01 pixel. So usually this ADMM only converges within 3 to 5 iterations. And if you want to modify what's the maximum iteration numbers for the ADMMM, you can easily just code, for example, the tolerance for the global step and also for the maximum of those AL soft step. You can increase this number from 5 to 3. And after that, you will have all the solved solution for the displacements. Yeah, this is how it looks like. And if you look at those ADMM iteration, you see quite nice convergence, those updated steps. And at the meanwhile, so you can just plot one more time. You can save all the temporary results, for example. Yeah, you can save some temporary results. So you'll be saved in a MATLAB file. So you saved all the DIC parameters you choose, for example, the DIC mesh, DIC para, and also all of those solved results like the displacements and the definition gradient of the F, which is the grid view minus identity, also the file name. And also because we do the ADMM iterations, so there's some temporary M files here. So if you run section 7, so all these temporary M files will be removed automatically. So I run this section. Yeah. So now you don't have those temporary M files. And you look at these results, you can double check what the parameter you choose. For example, so what's the DIC mesh use, and also this DIC mesh, there are the coordinates and elements, also the position. So you can easily to combine this with the additional element analysis. And for the DIC para, you see there's the window size, window step size, the image size, the ROI, the region for your image, you are select. Yeah. Okay, and then let's go to computer string. You can use the directly solved F, or you can smooth the displacement and then do the derivatives. So usually the ALDS already solved the results very nice. You don't need to apply additional smoothing filter. But you still can do it if you really want to do it. So let's run this section to ask you if you want to smooth the displacement. If you don't want to, you just input 1 or you press the enter key. If you want, you can press 0. So let's press don't want. Okay, and then you can select how do you compute those string. You can use the direct solved F. You can also use the finite difference or some plane fitting of an element to compute the derivative of the displacement. So usually I recommend 0 or 1. Let's choose 1. If you solve the solution that's super noisy, maybe you use some plane fitting. And you can choose what type of string you want to compute. You can use the infinite small string or Euler string or Lagrange string or some code by yourselves. So here we choose the small string. And you can save other figures into the JPEG or PDF or other format. So you can easily modify, go to the save fig files.m. So here we just save it to the JPG format. And you can choose what's the transparency to overlay with your original DIC images. Usually I just use half of those transparency. So after that, it will take just a few minutes to output all the images. Let's just wait a little bit. So usually you need to do the DIC analysis first, and then run the final section 8 for all the image frames. So after a while, you can see all those displacements and the string field it will overlay with the original images in the current deformed configuration. So sometimes you want to change those color bar for the C-axis, or maybe you want to change some other format of the images. So you can easily open these savefig files, and you can easily just code these images for their preferences, like their transparency, their color map, their C-axis. Yeah, it's quite easy. Just you can define them by yourselves. And then finally, don't forget to save all the results. So this will replace the one just after section 6. So finally save this one more time. So for your future use to double check your results, you can run this section one more time. And if you go to your command window, you have those JPG, and you will have the M file. Now I will show you one more time, but now we are not only solving 2 frames, we are solving the image sequence. So first, this image sequence in the example for those hip fracture. So if you open this in the folder, you can see how it looks like. Yeah. So basically, there are lots of those images for the hip fracture, and it's more than 1 frame there. So this is typical what you get for the image sequence from the DIC experiments. So before you start to run the DIC code, you need to add this subfolder, go to the path. Okay, and then we can just run one more time for the whole file. So this section 1, so I will first do the max setup. Okay. And then I will select the image folder. So this time, I'm not do the manually selecting image. I do the image folder. So I press 0 and press Enter key. And I select this folder. So I click Open. So all the images will upload automatically. And similar as before, the first is the reference image. So it will ask me to select what's the region of interest. So I click the top left corner point, and then click the bottom right corner point. And for the subset size, I use the same subset as before, so I use the 20 pixels. And for the subset step, I use half of those, about 10 pixels. And for the global step, I still use the finite difference. And I use the 2 parallel pools. Since we do the image sequences, so for the next new frame, you may not need to do the FFT for the initial guess again. So you can just use the last frame's results at the new initial guess, right? So now we can select 0, so use the last frame at the new initial guess. Or sometimes the last frame is not a good initial guess for the next frame. So definition is also huge between those 2 subsequent image frames. So you may need to redo those initial guess. So since this example, our image sequence, the time gap is quite short, so I just press 0. And you can choose do the cumulative or to the incremental mode, right? So here I use the cumulative mode, so where the reference image is always fixed for the first frame. So if you do the incremental, you may need to change or update the reference image after a few of those frames. So let's do the cumulative mode first. So same as before, the first 2 frames, we will do the FFT initial guess. So to maximize the cross correlation function, it's super fast because you the fast forward transform. So after that, you can see what's the output for the solve the displacement U and displacement V. Yep. So you will see those images pop out. And then you will do the local step, use the ICGN. So here I use 2 clusters. So most PC nowadays have more than 4 clusters, so you can try as much as possible. And for the bad points, about 1% for the first step of the ADMM. And then you can just manually select the upper or lower bounds. So you can see the ICGA is much better than FFT, right? And in this case, almost no bad points. So I just press Enter key or press 1 to skip all these steps. Yeah, and then there's the global step. And then we go to the ADMM iterations. Now you can see the local step that converges with all the subsets converge. So the ALDS had a much better convergence ratio than the ICGM algorithm. Sometimes if you don't want to see those images, since you are dealing with those image sequences, so you can just comment those plot functions. So for example, you can just search the plot. So all the function for the plotting, I start with a function called the plot. You can just comment these lines, for example, or you can comment some after the global step. There are also some plotting. You can comment those plot functions. So after the first frame computing, so now we'll go to the next one. So I use the last frame as the next frame initial guess. And it only have 1% local subset beta points. And I don't want to set up the upper or lower bound one more time. So I just press Enter key or 1. Similar that to the Enter key or 1. And then I will do the automatically for the global step and the ADMM for the next frame. So similarly, for the section 4, sometimes you don't want to always remove the bad points, right? So you can just comment those lines in the section 4. So here, between these manually find the bad points, just manually comment those. But there is some special case. There still needs to do some manual work since the image quality is super bad or something happens. You may need to still manually to remove bad points. So it really depends on what's the DIC image quality. So you can see all those ARDIC, the convergence ratio is quite high, about 100% subsets. So if you just use the ICGN, like you still have like 1 or 2% with not converge. Yeah, and then similarly, you can do this for the next frame. You can do this until you finish the job. And then you just run the section 8 again to output all the results for the string fields. So sometimes if you want to stop the run, you can just Control C, and you can rerun anytime you want to restart. And you can also easily change this for loop for where you want to start. So this code is quite easy to modify. It's not based on GUI, but once you are familiar with the MATLAB language and are familiar with the DIC algorithm, at least you know the FFT for the initial guess, and then the local steps, the global step, and the iterations. It's quite easy to modify. So once you solved all the frames, you save those M files here, and then you run the section 7 again to remove those temporary M files. Then you just run section 8 one time or compute all the frames for the string fields. And then you save those M file again. And then once you got those JPEGs, for example, here one of those, and then you can just combine those JPG images. You can make some videos for the displacement for the string. So for example, here the one of those displacement. So similarly for the string. And you can modify those string based on your choice. You can use the finite string or small string. If you have some problem, you can email me or email the aldicdvc@gmail.com. And besides the 2D ALDS code, we also have the volumetric ALDVC code. And if you are interested, you can just watch the video of the ALDVC. So finally, thank you for watching this video, and I hope you enjoy you applying your DIC method and outputting those very nice results for the fulfilled measurements.